Welcome back. I'm going to go back to what I was saying at the end last time about computing the shortest distance from a point to a plane. So remember, we're working in Rn, and we have an M plane, which is spanned by M vectors. We also have a given vector B, and we're interested in computing the distance from B to the plane. And that distance is given... There's also a point in that plane given by this vector v star. And we derived the formula for D, and I'd like to remind you how that works. So we constructed a bunch of things. So one of the things we did is we made a matrix A, which is an n by m matrix, made up of the columns of these vectors. That's an n by m matrix. And we also made the symmetric M by M matrix obtained by taking A transpose A. And then we defined a vector F, which was equal to A transpose B. And I want to be a little bit careful about the M's and the N's here. So A is an N by M matrix, so its transpose is M by N. So this makes sense and gives you an M vector, which I'll write as F1 through Fm. And I also defined the vector X star, which was just A times, X star, it was equal to K inverse applied to F, and this is an M vector, x1 through xm. And finally, define V star is equal to A times X star. And let's see, A is an N by M matrix, and X star is an M vector, so this is an N vector, y1 through yn. And I made a small mistake last time. I conflated X star and V star. So I want to straighten that out now. I'll put the final result over here. The final result is that we computed this. Well, vector V star is what I've indicated here. This vector is, in fact, the closest point in the plane to this vector B. And then the distance is, well, let's see, by the Pythagorean theorem, it's the length, I'll take the distance squared, is the length of B squared minus the length of V star squared. That's just by the Pythagorean theorem, and that's the length of B squared. And then the length of V star squared turns out to be F transpose K inverse F. All right, so in some sense this is the main result of the theorem. It's a formula for this number D, and it says it's the length of the vector B. The squared length is the length B squared minus this this thing here. And last time I neglected to mention V star directly. All I had was X star. I had this formula, although I believe I was missing the inverse. So in any event, this is the correct formula. And maybe I'll put a blue box around the V star, since this is the correct formula for V star. Okay, well, I want to go back to the same picture and reinterpret it just very slightly differently. So the way I was talking about it before was I asked you to find the distance from a point to a plane, and the plane was given as the range of this matrix A. In other words, I gave you the vectors v1 through vm describing the plane, and that's just the same thing as saying that this subspace is the range of this matrix, and A is a map from Rm to Rn. So let's just restate this problem very slightly as follows. So I'll state it sort of from scratch. We're working in Rn, and we're given a vector b in Rn. And I also have some m, and I have an m by n matrix, which I'm thinking is mapping Rm to Rn. And suppose I asked you to solve a times x is equal to b. Well, can you solve this equation? Yes, if and only if b is in the range of a. This has a solution. Has a solution if b is in the range of a, which is to say this point B is actually on this plane. And, well, suppose there's no solution. A reasonable next best thing to ask for is find the best you can do, which is to minimize ax minus b. So let's just look at this equation for a moment. This right here. So as x runs over all m vectors, this ax runs over all of the vectors in this subspace V. And if I can solve this equation, I can make this number 0. If I can't solve it, well, the best I could do would be to, if this is my b, is to take ax is equal to v star and get this distance. So in other words, minimizing this is just exactly the same question. And all I've done is restated it in a slightly different way. Okay, so what I was just talking about has a name, and that's called least squares. And so let me just summarize what I just said. Least squares is the following. Suppose I give you a matrix equation, ax is equal to b. Then the least squares solution is the x star, which minimizes the norm a x minus b. So that is to say, you look at all of the x stars, you look at all of these numbers that you get, and you take the one for which this is smallest, and that x star is called the least squares solution to this equation. And everything that we've just said gives you a formula for this. And I'll just state it. We've basically said it already. X star is precisely A transpose A inverse A transpose B. Okay, so I've proved this already. I'm just restating it. This of course is my K inverse, and this is simply my F, and that's the formula that I gave for Kx star a few slides earlier. One slight difference between this formulation and the previous one is that the focus here is on this X star, which is in Rm, as opposed to V star, which is its image in Rn. But that's just sort of a slight difference in emphasis. It's the same basic idea. one of the main applications of what we've just been talking about is the notion of data fitting and the least squares version of it. And the basic idea is the following. You're given a bunch of points which you've measured in an experiment, and you know that these points are supposed to lie on a straight line, except that there's some experimental error. What you want to do is find the straight line which best approximates these points. And what do you mean by approximate these points? Well, this line is supposed to be close to these points, and one way to measure that would be to take the vertical distance from each point to the line and call each of those distances di. And what you want to do is you want to find the line L, which minimizes the summation of the di squared. And it's natural to take the di squareds because you want to make them all positive. You don't want, and this is what's called the least squares fit. And what I'm going to do now is show how to calculate this using the techniques we were just talking about. So I need a little bit of notation. So I'm going to call this the t-axis and this the y-axis. And I'm going to suppose that these points are each a pair of points ti, yi. And this L that I'm looking for is some line given by y is equal to alpha plus beta t, where alpha and beta are to be determined. And what am I trying to do? I'm trying to minimize the summation of the measured yi's from the yi's on the line. And I'm squaring those. So this number here is yi is the y value for the point, and this is the y value on the line, and so this thing right here is what I called di. Here's the idea. We're given these points t1, y1 up to tm, ym, and I'm just going to define a couple of objects. I'm going to define the matrix to be the matrix with 1 in the first coordinate and the t's in the second. And I'm going to define a vector y to be the vector of the y's. And I'm going to define the vector x to be alpha and beta. And remember, this is what I want. I don't know what alpha and beta are. And notice that if the points are on the line, that would be saying that a times x is equal to y. Is that really true? Let's see. Why is that? So what is a times x? Well, that's 1t1 1tm applied to x alpha beta, and that's alpha plus t1 beta done to alpha plus tm beta. And to say that that's equal to y is to say that's equal to y1 through ym. And lo and behold, that's what it means. If y1 is equal to alpha plus t1 beta, that means that y1 is on this line, and similarly the rest of them. And, well, if not, how much are you off? Well, the error term, if you don't mind my using an eraser here, the error term is basically the difference of these two. Y1 minus this is this distance that I was talking about. This is your vector d1 through dm. And so if not, it's what you want to do is minimize the length of ax minus y. Okay? And notice that this is a 2 vector, this is an m vector. This is exactly the kind of thing we were just talking about. And we're mapping this A, you're supposed to think of as being a map from R2 to Rm. And the solution that we're looking for is this x star, which is in, oops, that's a 2. In x star, which is our alpha beta. Okay, so here's the result. We basically know what it is. Let's just write it out. I'll remind you, you're given these points T1, Y1 through TM, YM. And we're trying to find the best fit. A line L is alpha plus beta times T. The best fit is given by the following formula. Alpha beta is equal to A transpose A inverse A transpose applied to Y. And let's just do a sanity check on this thing. And this is one of these cases where you can sort of figure out what the answer has to be just because you have to figure out some matrix equation which makes sense. So let's see what this is. So y is this vector y1 through ym. Now what is A transpose? So remember A is this 2 by m matrix. So A transpose is a, I said wrong, m by 2, and then this transpose is a 2 by m. So A transpose is this 2 by m matrix. And then A transpose A inverse is what size? A transpose A inverse, well, that's this K that we've been talking about. And that's 2 by 2 matrix. So over here, you've got your A transpose A inverse, which is 2 by 2. And you put these all together, and what do you get? Well, when you multiply a 2 by m by an m by 1, what you get is a 2 by 1 matrix. Just a 2 by 1 matrix. And then you multiply that by this 2 by 2 matrix, and you get another 2 by 1 matrix, and that's your alpha and beta. So there's sort of a lot of calculation buried in this equation here, on these transposes and inverses and all these things. But it's actually just a direct application of what we had before. One thing I'll remind you of is that this thing here is what we've been calling K. And anyway, so I will do some examples of this in class.